Hey, this is section 3.4. In here we are continue to practice taking the derivative of things in the context of applications. So let's review some vocab words. Things that you're going to see in application problems: rate of change, marginal maybe I'll try to not write and talk at the same time. Marginal profit, marginal cost, marginal revenue, and population growth. All these things refer to the first derivative. So when you have applications and they're asking for one of these things, and velocity. When they're asking for one of these things, they're asking for you to take the first derivative. And then if they're asking for one of these things at a certain value, they're asking you to plug it in. That's the basic strategy. And then we've talked about this before. The other one you'll see is acceleration. This is the second derivative. Okay. Remember that the first derivative is the slope of the tangent line, okay, or the equation of the slope of the tangent line, depending on if you have a value or not. So that will navigate you through most problems. I'm going to do one example to get you started. A rocket is fired vertically. The path, remember we talked about the original function is often the position function. So the path is modeled by this function, s of t. T in physics land is always time. So, and then s is the position there for t equal time in seconds, and s equaling the distance in feet. Okay, so you get some labels on those things. Sometimes s is in meters or miles. It can be a lot of different things. So the question is asking first, what is the velocity 3 seconds after being fired? So physics was not my forte. I'll tell you what got me through physics was labels. So I look at this and I'm like, 3 seconds, that's a time. So I better be plugging that number in for t. So if you can just keep track of your labels, that'll help you a lot. If it gives you something in feet, then that means it's something that you're going to plug in for s. So that's really helpful and kind of guides you through the problem. So the first thing I want you to notice is that we are talking about velocity. So that's your indicator up here in your vocab words that we are going to do the first derivative. So I'm going to take this function, I'm going to find the derivative of it. The 2 comes down and hits that negative 16, makes this negative 32, t to the 1, because 2 drops by 1 power. And then 560t, that's just that drops down to a constant, just 560. All right. And then now that's the velocity function. Now I want to know what is the velocity after 3 seconds. So seconds is a time. It's going in here for t. So s prime of 3 is going to be negative 32 times 3 plus 560. And that's going to end up being 464 feet per second. I just check that math, but I think that's multiplied right. Okay. Part B is going to ask, when will the velocity be 0 feet per second. So look at the labels again, okay? First of all, the first derivative, when you take the first derivative, your label is always going to be distance over time, okay? And so your original function, this is going to be distance, this is going to be time, and the derivative is going to be your distance over your time, okay? So in part B, when I say when will the velocity be 0 feet per second, to me, I see this label and I go, wait, that's distance over time. This is my first derivative. So that means that I want to plug this in for s prime of t. See how I'm using the labels to figure out where to plug it in, okay? And so I'm going to now take, what this means is, take your derivative function and plug in 0 for s of t. Okay, and then you're going to solve it minus 560, negative 3t. So t is going to end up being 35. Let's see, I think it's 35 over 2 seconds. Okay, again, it's time. Okay, so it's in seconds. So here's this is the powerful thing, okay, about the derivative, and one of the most powerful things about these applications. Often in the physical world, we're interested in the highest or lowest point in something. So here's the picture. This rocket is fired straight up, okay, and then it comes down, and I want to know, how high did it go? Okay, and so that is the place where the rocket's going up like this at a certain speed. It's very fast when it's launched, and then it slowly starts to slow down because of gravity, right? And what happens at the top is it actually stops and then starts accelerating in the negative direction. So when I'm asking when will the velocity be 0, I'm asking where's the maximum of the function. And that's the powerful thing, because nobody's up there to be able to measure, but if you can figure out what the path is, the position function, you can take the derivative and find out the maximum height of the object. And so this is now telling us, hey, after 35 halves of a second, which whatever that is, I don't know, 18 something, somewhere around in there, after that many seconds, that's when the rocket will be at its highest. And that's how they're doing these calculations with space shuttles and all sorts of stuff like that, trying to figure out how high will these things go. Will they go high enough to do what we need to do? So that's one of the main applications of the derivative. I think that's pretty cool. So try some of those problems, and I will see you next time.